Hello everybody. Today's lecture will be on single photon emission computed tomography or SPECT and positron emission tomography or PET. Let's look at the objectives for today. After today's lecture, students will learn about SPECT instrumentation, image acquisition and reconstruction, and also SPECT quality control and corrections. Students will also learn about PET instrumentation, image acquisition and reconstruction, and also quality control and corrections. When we learn about attenuation corrections, which are introduced SPECT CT and PET CT, and finally end with a mention of PET-MRI. We learned a few lectures back about computed tomography, where X-rays transmitted through a patient in multiple projections is used to construct image slices through the patient. A similar approach can be done in nuclear medicine, where emitted photons from a radionuclide distributed in the body can be detected in different projections and used to construct image slices through the patient or object. This is referred to as emission computed tomography. When we perform emission computed tomography with individual or single gamma ray interactions in a crystal, it is called single photon emission computed tomography. When emission tomography is performed by detecting the annihilation interactions of photons released during positron decay, it is called positron emission tomography. We shall start with single photon emission tomography on the next slide. SPECT cameras may have single, dual, or triple scintillation camera heads. The heads may be arranged in parallel but will rotate to acquire projections about the patient at different angles as in standard planar projection imaging. If a single head is used, the head may rotate through 360 degrees. If a dual head is used, each head only needs to rotate through 180 degrees. Having multiple heads reduces the acquisition time for a given radionuclide activity administered. For example, if a single head takes 20 minutes to acquire projection images over a 360-degree rotation, having two heads cuts that time in half because each head only needs to rotate through 180 degrees. A dual head camera is shown on the left images and a single head camera is shown on the right image. In SPECT image acquisition, the camera heads may move continuously about the patient while acquiring image projections, or they may stop at predefined angles for each projection in a step and shoot mode. In cardiac imaging, the camera heads are oriented at 90 degrees to each other, and images are acquired over a 180-degree arc for better spatial and contrast resolution. For whole body imaging, the camera heads are parallel and travel through a 360-degree arc. The top image shows a cardiac image acquisition, and the bottom image shows the setup for whole body imaging. SPECT projection images are acquired in either a 64 by 64 or 128 by 128 matrix. When a 64 by 64 matrix is used, there are usually 60 to 64 projections, and a 128 by 128 matrix requires about 120 to 128 projections. During projection imaging, the camera head may move in a circular or elliptical orbit. In some SPECT systems, circular orbits are used for brain imaging, but causes a loss of spatial resolution in body imaging because the body is non-circular and the camera heads are farther away from the body surface at points in the image acquisition process. To avoid this issue, newer SPECT systems provide an option for non-circular orbits like elliptical and body contouring orbits to keep the camera heads as close to the body surface as possible during imaging. The images show circular and body contouring orbits. After images are acquired, they are corrected for non-uniformities and center of rotation misalignments and errors before reconstruction using either filtered back projection or iterative reconstruction. In filtered back projection, the images are first filtered using a ramp filter together with a roll-off at different frequencies as the graphs show. If only a ramp filter were to be used, the images will contain high amounts of statistical noise which predominates in the high frequency portion. So the roll-off at high frequencies allows the image to be smoothed before reconstruction. So there is a compromise between spatial resolution and image noise. The top picture shows a SPECT image created using different filter kernels. The first image shows too much smoothing, which corresponds to filter A in the graph below. The middle image showing proper smoothing corresponds to filter B, and the image at the top right showing no smoothing corresponds to applying just a ramp filter as shown below. While filtered back projection imaging is computationally efficient, it assumes that projection images are perfect representations of the object being imaged. In scintillation camera imaging, this is not true because of photon attenuation as it travels through tissues, the presence of Compton scattered photons from the energy window, and the loss of spatial resolution due to the camera head distance from the object. Iterative reconstruction is another image reconstruction method that uses assumed radionuclide distributions to calculate projection images from a mathematical model. The model takes into account the imaging characteristics of the scintillation detector and the patient attenuation characteristics if available. The calculated projections are compared with measured projections and adjustments made. This process is repeated multiple times in a process called iteration until there is minimal difference between the calculated and projection images. I mentioned on the previous slide that when iterative reconstruction is used for reconstructing images, projection data is calculated from an assumed radionuclide distribution using a model of the imaging characteristics of the scintillation camera and patient attenuation characteristics if available. Because patient attenuation characteristics are not always available, approximate methods are sometimes used for attenuation correction. The Chang method assumes a uniform attenuation in the patient and uses attenuation coefficients of various strengths as shown on this image. Another method is to acquire transmission data around the patient using a sealed source radionuclide like gadolinium-153. The transmission data is used to create an attenuation map for the patient that is used for attenuation correction of the iterative reconstructed SPECT projection images. Patient attenuation characteristics can also be obtained by first performing a CT scan of the patient and using the CT attenuation data to correct for patient attenuation. This is done when a SPECT system comes with a CT scanner in tandem. These systems are called SPECT CT systems. Because SPECT cameras acquire projection data around a patient, quality control is critically important. In planar imaging, equipment malfunctions or maladjustments may not be noticeable, but in SPECT imaging they can produce significant artifacts that mimic anatomy. In addition to the tests done for planar imaging, XY magnification factors tests can be done to ensure the camera magnification is the same in the X and Y planes. If magnification in X and Y planes are not equal, coronal, sagittal, and oblique images appear distorted. Also, when imaging multiple energy radionuclides, the multi-energy spatial resolution test ensures the images have the same magnification regardless of the radionuclide used for imaging. When SPECT images are acquired, the camera rotates about the patient while acquiring projection data. If a source of radioactivity in the patient is imaged incorrectly in the image matrix for different views, it will appear as a ring in the final image. To verify the center of rotation, a point source of activity is placed at the center of rotation and imaged from multiple views. In each view, the source will appear in an individual pixel. The pixel in which the source appears should be the same in views taken from different angles so that the image appears as a dot on the screen. If the center of rotation is slightly misaligned, the dot is blurred, and if the center of rotation is largely misaligned, the dot appears as a donut. The images here show the various levels of misalignment. There are SPECT quality control phantoms that can be imaged periodically to evaluate system performance. The JZAC phantom is commonly used for performance evaluation. It is filled with a clinically used activity of technetium-99, imaged and processed with a clinical whole body protocol. Image quality is evaluated for uniformity, spatial resolution, and contrast. This table shows a suggested schedule for SPECT QC. Aside from the QC tests done to ensure the system is functioning correctly, corrections can also be done after images are acquired to improve image quality. Corrections can be done to account for patient or organ motion, center of rotation misalignment. There can be corrections for attenuation of the patient and also non-uniformity corrections. Corrections for scatter and also for spatial resolution losses can also be done. Non-uniformities, whether from the camera or collimator, show up as a circular artifact in the reconstructed image if not removed by non-uniformity corrections. This image shows a ring artifact due to non-uniformity. Non-uniformity corrections are done with a high count flood of 30 million counts. These flood data must be acquired with the same parameters such as photo peak window, zoom, and collimator that is used in the clinical study. The center of rotation information used in the reconstruction process must be corrected to avoid data misalignment and artifacts. The center of rotation is measured with a point source and the correct center of rotation established. Projection data is first shifted by the difference between the center of rotation and the center of projection matrix before the reconstruction process. Body motion can be tracked using fiducial radioactive markers. Any change in patient position will show up well in the sinogram data of the markers. The projection data are shifted as appropriate in order to correct for body motion. Fiducial markers cannot correct for internal organ motion. Organ motion is corrected by properly positioning the organ in the projection data. Because photons travel through layers of tissue before exiting the patient, correction for attenuation is important. A simple attenuation correction can be done by using Chang's method, which assumes a uniform phantom with a linear attenuation coefficient. The most accurate methods of correcting for attenuation involve the use of an accurate 2D attenuation map. This 2D map can be obtained with a sealed source radionuclide during a transmission scan or with a CT scan of the patient prior to SPECT scanning. Photon scatter in both the patient and the collimator gives rise to image blurring and can lead to inaccuracies in quantification. With a standard 20% photo peak window, approximately 30% of counts in a technetium-99 image come from scattered photons. Corrections for scatter can be done in a simple way by using an experimental value for the linear attenuation coefficient. This method oversimplifies the problem. Other more sophisticated methods are available that involve the convolution of 2D and 3D point spread functions. This image shows the effect of a 3D deconvolution scatter correction method on the spatial resolution of a phantom image. Other more sophisticated methods involve the use of Monte Carlo modeling. One way for sites to ensure they are running a quality imaging program is to obtain accreditation from an accrediting organization like the American College of Radiology. The steps involve acquisition and submission of both clinical and phantom images for review, as well as the most recent physics report. Phantom images are evaluated for image quality when acquired using an activity commonly injected for clinical studies. The ACR online testing package submitted by the facility is shown. The Joint Commission on the Accreditation of Health Organizations (JCAHO) is a standard setting and accrediting body for healthcare organizations. Healthcare organizations and hospitals can earn a gold seal of approval from the Joint Commission if they undergo an on-site survey every 3 years. Let's now turn our attention to positron emission tomography. Unlike SPECT that uses projection data acquired from a rotating scintillation camera head to create images, PET uses projection data acquired from the coincidence detection of annihilation photons acquired from a ring of scintillation crystal detectors positioned around a patient. Special coincidence detection circuitry is used for this purpose. Because annihilation photons are emitted at about 180 degrees apart, the presumed directionality of these emissions as they arrive in coincidence at two detectors is used to localize the origin of the photons. The PET system's computer then reconstructs the transverse images from the projection data. The image here shows two collinear photons emitted during an annihilation interaction as shown here. And those two photons are detected in coincidence at two detectors along this line called the line of response. Coincidence detection circuitry uses a timing window for coincidence detection of photons arriving at detectors along a line 180 degrees apart. The timing window is the designated time interval during which a pair of interactions in the different detectors is considered to be in coincidence. The duration of the timing window used depends on the type of scintillation material used for the PET crystal. Some scintillators like LSO have very short decay constants so emit light promptly. The timing window for a scintillator using LSO is 4.5 nanoseconds, compared to scintillators using BGO, which is 12 nanoseconds. The properties of various scintillation crystals used in PET is shown on this table. Once the timing window is set, counts can be detected. Counts are classified as true counts when they are in the coincidence timing window and along the line of response, the solid line shown on this image. In scatter coincidence, counts arrive at two detectors 180 degrees apart but are on a line of response that is due to multiple scatter events. In random coincidence detection, counts arrive in coincidence at two detectors 180 degrees apart but are due to two separate and random events as the line of response shows. PET imaging could be inherently tomographic if the exact location an annihilation event occurred could be accurately determined. This is done by knowing the exact arrival time of annihilation photons. With newer PET scanners with time resolutions of about 3 nanoseconds, more accurate localization is possible and is utilized for time-of-flight PET imaging to improve image quality, especially the signal-to-noise ratio when incorporated into the reconstruction algorithm. PET data may be acquired in 2 dimensions or 3 dimensions. In 2-dimensional data acquisition, axial septa made from tungsten are used to prevent radiation outside of the transaxial slice from reaching the detector ring for that slice. This is shown in the top image. In 3-dimensional data acquisitions, septa is not used, and data is collected across many or all of the detector rings as shown in the bottom image. There are advantages and disadvantages to both systems. In 2-dimensional acquisition, scatter is reduced, but sensitivity is also reduced. In 3-dimensional acquisition, sensitivity is greatly increased, but so is random and scatter coincidence detection, and also there is an increase in dead time count losses. Some PET systems are equipped with retractable septa to allow both 2- and 3-dimensional acquisitions. The most effective way to deal with random events is to design the scanner to limit random coincidences. This can be done by using shielding or by using detectors with short temporal resolution times. Randoms can then be reduced by subtracting them from the true coincidences. Scatter coincidences can make up to 30% for a 2D whole body image and can be even higher for a 3D whole body image. Scatter can be corrected by mathematical approaches that involve the convolution of a non-stationary scatter response function or by modeling the scatter distribution with a Monte Carlo method. The spatial resolution achievable in a clinical whole body scanner is typically between 5 to 10 mm full width at half max and is about 2 to 3 mm in a brain imaging system. Spatial resolution decreases slightly as you go away from the center of the PET ring. Spatial resolution is limited by the crystal width, which determines intrinsic spatial resolution for the crystal detectors and the distance traveled by the positrons before annihilation or the positron range. It is also limited by the fact that the photons are not emitted at exactly 180 degrees apart, so there is a non-collinearity effect. This aspect of spatial resolution loss increases with the diameter of the PET detector ring. By designing PET systems with smaller detector rings and using thinner crystals, spatial resolution can be improved. Design of smaller detector rings worsens the off-axis radial resolution. To correct this, photosensors are used at each end of a crystal to detect the light output as a way to determine the interaction position within the crystal. Another method involves using pulse shape discrimination to identify different decay times. In PET, attenuation is more severe than in SPECT because of a higher chance that the photons passing through tissue will interact before exiting the tissue. Attenuation correction in PET can be done as in SPECT by using attenuation coefficients based on a uniform phantom. Another method is to use a transmission scan using a retractable germanium 68 rod source. The transmission scan is used to correct the emission data before image reconstruction. The top image shows the use of a rod source for acquiring the transmission scan data used for attenuation correction. The bottom image shows 2 images, one with no attenuation correction and the other with attenuation correction. In current whole body scanners like PET-CT systems, the CT data are used to provide an attenuation correction for the PET scan. Usually the CT scan precedes the PET scan and the quality of the CT image required depends on the CT technique used in the X-ray system and the time taken for the scan. It should be noted that the radiation dose to the patient from the CT scan may be comparable to that for the PET scan. The effect of the energy difference between the photons from the CT scanner and the photons from positron emission is corrected prior to applying the CT-derived attenuation correction. To ensure a PET system is performing to specifications, quality control is important. A few quality control procedures are listed here. Quality control tests are done with a specialized PET phantom. We shall start with normalization and blank scans on the next slide. A normalization scan is done to correct for variations in sensitivities between different detectors or detector pairs. It is equivalent to the uniformity correction of a gamma camera performed with a flat phantom. A normalization correction in PET is done by obtaining an image of a rotating pin source or a uniform cylindrical phantom. Normalization is acquired quarterly or after system maintenance. The top image shows a scan performed without normalization on the left and one acquired with normalization on the right. A blank scan is done to correct for random variations in detector efficiencies that often lead to an increase in noise and artifacts in reconstructed images. A blank scan, which is a transmission scan with nothing in the field of view, or a scan performed on a uniformly active cylinder, is first performed. An attenuation correction factor is obtained and applied to every line of response in the emission sinogram. The correction factors obtained are then proportional to the inverse of the count rates obtained for each line of response. A blank scan can be done to validate the normalization scan. Uniformity is important in PET imaging, just as in SPECT imaging. Uniformity is the scanner's ability to accurately reproduce the activity in the field of view. Procedures for uniformity involve measuring the uniform activity in a phantom and analyzing a 15 cm region of interest in the image. A mean and standard deviation of pixels in the region of interest are obtained. The phantom used for PET imaging is the JZAC Deluxe Flangeless Phantom with the spheres removed. This phantom contains a section for contrast evaluation, a section for spatial resolution, and also a section for uniformity evaluation. The phantom is imaged using an activity of FDG used clinically and processed using a clinical whole body protocol. The phantom is then analyzed for uniformity, spatial resolution, and contrast resolution. Once the phantom is imaged, a semi-quantitative index is used to assess performance. The standardized uptake values, or SUV, is defined as the tumor uptake in megabecquerels per milliliter to the injected dose in megabecquerels per patient weight in grams. This index assumes that a uniform radionuclide distribution will produce a SUV of 1 everywhere. The top image is the JZAC phantom, and the bottom image is a contrast section of the phantom showing the measurements of the SUV values. Sites performing PET imaging can obtain ACR accreditation as evidence of a well-run imaging and quality control program. ACR accreditation involves acquiring both phantom and clinical images and uploading them for evaluation. The phantom images are analyzed and SUV values obtained. The top image shows the region of interest used for SUV analysis, and the bottom image shows images of the phantom submission. As in PET-CT, when PET imaging is combined with MRI, the MRI system provides tomographic images with excellent depiction of anatomic detail, and the PET information is spatially co-registered with the MRI information. The MRI information is also used to estimate attenuation coefficients in each voxel of the patient for correction of the PET information for attenuation of the annihilation photons. The main problem with combining PET with MRI is with the use of photomultiply tubes in the PET portion of imaging. Photomultiply tubes contain moving electrons that are affected by the magnetic fields of the MRI system. The solution to this is to use avalanche photodiodes in those PET systems that are integrated into the MRI system. If the PET system is separated from the MRI system, then the photomultipliers can still be used. This is done with systems where the PET and MRI are imaged sequentially. Thank you for watching this presentation.